Hello, in this video we are going to discuss the Titan or Romec constant displacement engine driven fuel pump. Alright, so what makes this pump work? Let's take a look at it. First thing I want to talk about is just the very basic pump, which if we take it down to its basic component, it's just a pump with an inlet and an outlet. And so right here, as it's labeled, we have an inlet and fuel would enter this area right here. And here we have a rotor with some vanes that slide in and out. So these vanes right here are either steel or it can be carbon. And what happens is this rotor will rotate around. The engine will drive this rotor, allowing these vanes to slide around inside of the rotor, creating both small areas and large areas, or voids, if you will. So as this turns around, you will see that fuel comes up into here, and it is pulled by these vanes rotating around. And so it'll be pulled up into this chamber right here. And then as this vane rotates around, we'll have another chamber here. But as it starts to come around this way, what happens is it starts to get smaller and fuel has nowhere to go. And so the fuel is then forced out and through here down to the outlet. So let's take a look at an actual pump here that I've taken apart, and you can see that this right here is the rotor that fits down inside of there, and here are the vanes that would slide around, and here's that little pin that's right in the middle. So we would look at it like that, and that allows the vanes to move around inside of this eccentric hole. And so that is going to, I'll put it in correctly, we'll set that in just like that. And now you can see how if this is the inlet coming in this way, how as it goes around, the vane right there would come around, and because there's no space right here, it's going to force fuel to go that way out the outlet. Let me put the vanes in here and we'll take another look at it. Alright, so I've inserted the vanes in there, and now we can take a look at it. So we'll rotate it around, and we can see how the vanes will slide and move as we rotate this. So the way I'm rotating it right now, this would be the inlet side right here. So fuel would come in this way, be drawn through here, and as it enters this chamber over here, you can see how the space gets very small. Fuel has nowhere else to go, so it's going to be forced out the outlet right here. Now if I turned it the other way, we would just have the inverse of that. This would be the inlet side, and the same thing would happen. Have a space here, but the space gets very tight right here, forcing fuel out that way. So that is really the very basics of the pump and what it's doing and how it pumps. So while we're talking about rotation, it's important to note that when we talk about the rotation, it's not viewed from this end, but fuel pumps or really any engine driven accessory, whether it be a fuel pump, magneto, or whatever you have attached to the engine. We'll look at this pump right here. The direction of rotation is when viewed from the drive end. So this is the drive end. And so if we rotate it this way, it would be a clockwise rotation. And if we turn it this way, it would be a counterclockwise rotation. So all right, that's the basic pump. Now let's add some accessories to this pump, because in its current state, it's completely unusable for any purpose we would have in aviation, because as I mentioned, it is a constant displacement pump. It will put out a certain amount of liquid for every single rotation. And that means that as this turns around, it is going to put out the fuel that is in this cavity out this way. It absolutely has to do it. There's nowhere else for the fuel to go. If I were to block off this outlet, fuel would not just slip around through here and the pump would be okay. It would not. It would destroy the pump. It would actually shear the shear shaft, it would break vanes, it would do some significant damage to the pump. In the same way, if I had a hose that was connected to here and we blocked off the end of the hose, it would probably either blow up the pump or blow up the hose. So we can't just have a pump that is forced to pump out a certain amount of fluid with nowhere to go, because on the outlet side of the pump, we have to think future. We're going to have some sort of fuel control, either a carburetor, pressure carburetor, fuel injection system that is going to be regulating the fuel. So we have to have a pump that will allow fuel to be bypassed and not destroy the pump. All right, so the item that we're going to talk about right now is the pressure relief valve, but it's really designed so that there is a a function where we can regulate the outlet pressure of the pump. And the way that is done is through this pressure regulator that is going to sit on top of the fuel pump. So let's talk about the components of this. So first of all, what we have inside of here is a diaphragm. So we have a diaphragm. On top of the diaphragm, we have a spring and a control. Oh, there goes my spring. Spring and a control and a locking ring up here. So all put together, there it is. All right, so back over here to my one that is disassembled. So the way this works, and we'll look at the drawing first here, is we have fuel is going to come into the inlet. Fuel cannot go up this way. It is blocked off. When this bypass is closed, it would just fill up this chamber and there would be nothing happening. But fuel comes in this way. The pump rotates, forces fuel to go out the outlet. Remember, it's forcing it. The fuel now has two choices. One, it can go out the pump outlet to our fuel control unit, or when a certain pressure has been met, fuel will then go up this way, pushing on the bottom of this poppet valve, forcing it up against the spring and diaphragm pressure and allowing fuel to bypass and work its way back to the inlet side of the pump and just recirculate. So in this case, if I actually blocked off this outlet, fuel will just come this way and recirculate around through the pump continuously until such time as something changed. All right, so let's take a look down here at how this works exactly in all of the components. So here's our pressure relief valve assembly, and this is the diaphragm that sits on top, and underneath that we have a poppet valve. So there's the poppet valve right there, and so that sits on this shaft. And the way it works is this cap right here always represents the discharge side of the pump. So fuel would come into the discharge side of the pump because that's the pressure side. It'll go into this cavity right there, which is not connected to this at this moment. It is blocked off by the poppet valve. Fuel pressure comes in here, pushes on the bottom of the poppet valve, pushes the poppet valve open against the diaphragm and the spring pressure, and then is allowed to come through the bottom of the poppet valve and now out through here. So again, it comes in this way, poppet valve opens, comes into this chamber, which is now open down there, allowing the fuel to come this way back to the inlet side of the pump. So this would be the outlet side, comes up, around, back to the inlet side of the pump. So it just recirculates right through there. And by the way, if I took and I put this on this way, then everything is just reversed. This becomes the inlet side of the pump and everything works the same. It's just the pump has to turn in the opposite direction. So all right, getting back to this right here and how this works exactly is that we have this diaphragm here with the spring and an adjustment on the top. So what happens is this is a locking ring. So when it's together, we just tighten it up. You cannot move the adjustment. So we just back that off a little bit and now we're free to turn the adjustment. So the adjustment, and this confuses some people because it has left-hand threads, and you see if I went to loosen it, like to take the nut off, it just got tight. But if I try and tighten it, it makes the nut go down. But don't let that confuse you. It's actually built that way so that you can intuitively think about how things work. When it's assembled inside of here, it's going to hold that nut steady. And if I want more pump outlet pressure, that means I need to make it harder for the fuel to push up on that poppet valve. So that means I want more spring pressure. And if you just look at the nut and you think, well, which way would be more? I would think this would be more and this would be less. So if I want more and I turn it this way, what does it do? Well, it actually forces this nut down and puts more pressure. And if I think about it, well, if I want less pressure, I'll loosen this. When I loosen that, then it lets this nut come up this way, decreasing the spring pressure, which makes it easier for the fuel coming out of the discharge side of the pump. Well, do it this way, discharge side of the pump, to push up on the poppet, overriding the spring pressure and the diaphragm pressure, lifting up this poppet valve, allowing more fuel to recirculate. So that's how we adjust the outlet pressure of the pump. Right, in addition to the spring, there is a port right here. This is a vent port. And what that does is it vents air to the top of the diaphragm. So it is sealed off from the fuel, and it is attached to a vent that is going either to vent to just atmospheric air or to upper deck pressure if it is a turbocharged or supercharged engine. And upper deck pressure is just another way of saying the turbo outlet pressure before it gets to the throttle valve. So let's talk about just a normally aspirated or non-turbocharged supercharged engine and what this is doing. So if we did not have a vent here and it was capped off, then if you think about it, when I assemble all of this and I get an airtight seal in there, then the spring and diaphragm would always have to overcome air pressure that has been trapped inside of here. And that would not be a good thing, because as we go up in altitude, that would be more of a nuisance or have more of an effect. So also, now by having it vented, when we're down here at lower atmospheric pressure, we would have our atmospheric pressure at sea level being 29.92 inches or 14.7 psi. That would give us a little bit more pump outlet pressure. And the opposite would be true. As we go up in altitude and air pressure is decreasing, then that would mean that we have less air pressure on top of the diaphragm, which is not assisting the spring, which would mean that the fuel pressure being generated by the pump would allow this to rise up a little sooner, decreasing our fuel pressure in a normally aspirated engine. But let's talk a little bit more about if it's a supercharged or turbocharged engine. Then this is vented to upper deck pressure, which is, again, the turbocharger or supercharger outlet. And so there, especially in turbochargers, there's a little bit of lag in that pressure. So this would be an assist to that. But what happens is, as the turbocharger or supercharger spools up, then that is going to create more pressure in the upper deck, which eventually leads to more pressure inside of the manifold going to the engine. Now, as that pressure builds up, we're going to want more pressure out of the pump to the fuel control unit. So the turbocharger spools up, puts pressure inside of here, turbocharger pressure now, which presses down on this diaphragm, which assists the spring, which increases the outlet pressure of the pump. And if you think about, if we talk about turbo lag, it may take a while for the turbocharger to actually spool up. So if we were to add the throttle to the engine's going to speed up. The pump is attached directly to the engine, so the pump is going to speed up. So the pump is now going to start putting out more pressure, more volume, but we're really not ready for the pressure to go up yet because the turbocharger hasn't spooled up yet. So we want the pressure to stay reasonably low or stay the same until the turbocharger spools up. Now, once it spools up and then puts pressure in here, at the same time that the pressure it spooled up, we got pressure here. Now we're getting pressure across the throttle valve going into the manifold, and now we're ready for more pressure. So until we're ready for more pressure, we don't want it, and tying it into the vent right here does assist in timing that with that. So once again, just because I know that was a little confusing, when it is not turbocharged or supercharged, it's just vented to atmosphere. And the atmospheric pressure down low would have a little assist on here, and then when we go up in altitude and the air pressure decreases, it would be less of an assist. And when the vent plug is attached to a turbo or supercharger upper deck, what happens is we add more throttle, the engine is going to speed up, the pump will speed up because it's attached to the engine, but the pressure from the turbocharger has yet to spool up. So the pump will just speed up, and the outlet pressure would remain exactly the same because nothing has changed up here. But as the turbocharger spools up, creates more pressure in the upper deck, which then creates more pressure in the manifold, which means we want a little bit more pump outlet pressure. Then at the same time, that pressure is transferred into this port right here, which presses down on the diaphragm, which assists the spring, causing the outlet pressure of the pump to increase. All right, let's move on and talk about the bypass valve. So the problem with this pump is that we need to get fuel through the pump to start the engine. We need fuel to go from the boost pump in the fuel tank across this fuel pump into the fuel control unit, so we get fuel to start the engine, and then once the engine is started, the pump will start rotating. Well, true, the pump does rotate with the starter, but it's not enough to give us the fuel we need to get going. And we have to consider the fact that what would happen if this pump were to fail? We still need to get fuel through the pump into the fuel control unit. So looking at this drawing, the way that works is fuel would come in the inlet right here. It would go up through here, and this talks about the bypass valve plate. There are holes drilled right here and a spring, a very lightweight spring, so that when fuel came through here, it would push down on this plate, allowing fuel to go around the pump. Let's take a look at another picture right here that just shows this particular plate now being open. So with this pump in the off position, we would turn on the boost pump from the fuel tank. Fuel would come in through here, not be able to go past the vane, so it's locked. It can't go this way at all, so the fuel will run up this way, and pressure from the boost pump will force this plate down against a pretty weak spring. It even says weak spring. Down through here and out to our fuel control unit. So this would be in the pump in the off position, so if the pump were to fail, or the engine is not running, this is how fuel would get through the pump and off to the fuel control unit. But now let's take a look at our actual pump, because our pump is different than the drawing. Same concept, but it is different. So inside of our relief valve up here, we have a bypass valve. And I'm going to open this bypass valve up here, but we'll take a look at it here before I get too far. And this is the pressure side of the pump, all right? So what happens is we have this on the outlet side. That makes this the inlet side. So we have fuel comes up into here, and it's allowed, even with the poppet valve closed, into this chamber right here. So fuel from the boost pump came up through this way, filled up this chamber, and went to the back side of this valve right here, which I will take out. And on the back side of this valve, we have the weak spring, which is, compared to that one right there, is very weak, with this little poppet valve here. And that little poppet valve is sitting against a seat inside of here. And so as soon as we get any sort of fuel pressure from the boost pump, not this pump, the boost pump in the fuel tank, it will push open this valve right here, allowing fuel to come out of this and then bypass out this discharge side. So inlet comes up through here because it can't go through the vanes, across the top, pushes against this, and out to the discharge. Now it's going to continue to do that until such time as the pump pressure here exceeds the boost pump pressure. So even if this was turning very slowly, it would not, turn this way, it would not put out very much pressure. So this would continue to stay open as long as the pressure coming in this way was more. But once this pump gets going and it has more pressure than the boost pump, remember this is the outlet side now, so more pressure right here than the boost pump, that pressure is going to come back here, assist the spring, and now force it closed against the seat. So once this pump outlet pressure exceeds the boost pump, then it's going to close this little valve off inside of there, and the boost pump will no longer be able to bypass this bypass valve right there. So that's a bypass valve. Remember, it's there for two reasons. One, to start the engine, and two, in case this pump should fail. All right, let's move on and talk about some of the drive and components of this particular pump. So remember, the drive, direction of rotation is when viewed from the drive end of the pump. And so this would be clockwise and this would be counterclockwise. And let's take a look at this shaft. And we talked about the fact earlier in the video that if there was a blockage, the pump could actually disintegrate or fail or have some sort of catastrophic failure. And right here, notice how this drive shaft has been necked down, pretty small. This part right here is considered a shear shaft. So if the pump were to have a failure, a blockage, some sort of failure, we do not want this transferred through this drive end into our engine, causing damage to the engine. You want to separate the two. So if this were to lock up, it would shear right here, break right here, allowing this shaft to continue to turn and this part of the shaft to no longer turn. So this is our drive shaft, and our drive shaft has to be sealed from the engine because on this side we have oil and on this side we have fuel. We do not want the fuel from the fuel pump making its way back into the crankcase and causing some sort of problem with fuel leakage into the crankcase. That dilutes the oil and creates an explosion hazard in the crankcase. All right, so the way this seal works is like this. We have the shaft, and we have a dynamic seal right here, which is basically a metal-to-metal seal. We have a diaphragm here with a piece of metal here. We have a slinger ring inside of here, and then another little copper piece right there. So this goes together this way. This is going to go through this assembly here where we have metal-to-metal contact between this slinger and that right there. That all goes together, and it is pushed together with a spring that ultimately is on the rotor side inside of there. So the rotor is going to push against that. The spring helps this metal-to-metal contact, and that should keep fuel from entering the engine. Now, some fuel can get through here. A little bit may get through there. And so what happens to any fuel that gets through this right here then enters into this chamber right here. And this chamber right here then leaks out through these slots. These slots are connected to these holes right here. Some of these holes are screw holes and the other ones are drain slots. And these drain slots are then corresponded to these 4 ports right here. The reason why there's 4 ports is because this pump can be put on in any one of 4 different directions. And what you want to do is make sure that so if it's mounted this way, we'd want the lowest one right here unported, and that would then be a drain that would go overboard. So we don't want to just pull out a plug and then let it drip onto exhaust or turbocharger. That would be a significant fire hazard. So we plumb this to overboard, and we can tell that we would have a leak because it would leave a little blue stain from the 100 low lead fuel. So again, if we put it on in this way, then we would take out this plug, put it over here, so this is the lowest point and that is out. So that is how the dynamic seal works on that, and that is in fact the Titan or Romec constant displacement fuel pump.